Okay, we're getting our first introduction to flux. Flux is spelled F-L-U-X, and it's the Latin word for flow. Now, although it involves velocity, it's not velocity, because it's not asking us how fast something is moving. It's asking us how fast an amount of something like liquid is actually changing. Let me give an example, and then we'll look at the units and try to describe it a little bit better. Suppose I have a big square region or rectangular region up there that's like by 2 feet by 3 feet like this, and water is just flowing directly into our room at say 5 feet per second. So let's call this 5 feet per second. Let's call this 2 feet. Let's call this 3 feet. Now the flux would be the volume of water that would actually enter our room in 1 second. Well, that's going to be the 5 feet per second times the area of that region. So this can be 2 feet times 3 feet. And so you can see that the units are going to be 3 feet cubed per second. So it's how fast the volume of water in the room is changing, not actually how fast the water is flowing in feet per second. So that's at least a description of flux. Let's change the region just a little tiny bit, at least in only one significant way. If I now have a region that's sitting over here, but it's still actually in the YZ plane, and it still has area of 6 square feet. And if the water was still flowing exactly as it was before, directly into the room, sticking out of the YZ plane at 5 feet per second, in terms of the calculated flux, nothing's changed. So it wasn't the shape of the region that was important. It was very important that it was flat. It was very important that the flux all kept coming at the same direction. A couple things that actually resemble projection. If this is still 2 feet, this is still 3 feet. And now, if the water is now going back out of the room, well, that should be different somehow. And so that actually brings up the first thing we actually have when we have a region. We're going to have to designate one side as positive. In this particular case, I'm going to say positive is actually into the room, like this. And so if the only thing that's changed is that the velocity vector of the liquid is now the other way, the flux is now going to be, ready, negative 5 feet per second times the 6 square feet, and we would get our negative 30 cubic feet per second. And so you can see that flux can be negative if water's leaving the room. It can be positive if water's entering the room. And just like with projections, flux can be zero. Flux can be zero, right? So if I have exactly the same region again, this is still 2, this is still 3. What happens if the water is now just sitting in the YZ plane, never entering the room, never leaving the room, right? Then because we designated positive as entering the room, the flux here, yes, would be the velocity of the water entering the room. Well, the velocity of the water entering the room would be 0 feet per second. Like this, and so we would get a flux of 0 cubic feet per second. So we can see it's very, very important which direction the velocity vector is going and whether it's actually going in our direction at all. Finally, to get the more general situation that we need to start with actually, let's say that we still have our 2 foot by 3 foot thing here. So this is 2 feet and this is 3 feet. And let me just draw a little box here so you can visualize what's going to happen now. Let's go like this, and let's suppose the velocity vector starts at the origin and ends up at this corner, up like that. And the length of the velocity vector is still 5. Well, it's not going to be 5. It's going to be whatever it is. hold on a second. If this is actually, well, we haven't said how far to go in here. Let's say we go 10 over. We'll go 10 over like this. Then the length of the velocity vector is going to be the square root of 2 squared plus 3 squared plus 10 squared. That's 4 is 113. Square root of 113, which is a little bit bigger than 11, like this. Now, the velocity, the flux is not going to be the square root of 113 times the 6, because not all of the 113 is actually headed in the direction that we've designated as positive. So what we absolutely have to have is a normal vector, something that's sticking straight out of our region. And then we need to know how much of the velocity vector is actually going in that direction. So what we need to do is take our velocity vector, and most of our vector fields have been designated like that, so that's our velocity vector, and then we need to dot it, like this. Remember, that's the projection formula. So this is actually what velocity the vector field is actually entering our room, and then when we're all done there, we would want to multiply by the area. In this particular case, the velocity here looks like it's going to be 10, 2, 3, like this, and we're dotting it. We want to dot it with a unit normal that's headed in the I direction, so that's just going to be 1, 0, 0. And then when we're all done with that, we would want to multiply by the area of the region. So in this particular case, we would have a flux of 60 cubic feet per second. But this is the important thing. If we have velocity vector that's not going directly perpendicular to our region, then what we have to do is find out how much the velocity is actually going perpendicular to our region in the positive direction. And when we're all done with that, we'll actually get the velocity of the stuff entering the room, and then we multiply by the area. So this is actually the heart of where calculating flux for us will begin.